A very good afternoon to everyone. Today we'll start with the first topic, that is basics of open channel flow. So in this, we'll be discussing what is open channel, what are the characteristics of open channel, and then we'll differentiate between open channel flow and pipe flow. What are the types of channels and types of flow? With that, we'll summarize our discussion today. So as I've already given you the introduction of open channel flow in the first lecture, so here we'll be discussing more into detail. So technically, the open channel flow covers the range of natural and artificial conveyances of water in settings that are open to atmospheric pressure. So you have those natural and systems, like you have a water flowing in the creeks or rivers. Creeks are usually those water bodies which are connected with the sea. So there you have some backwater flow. So that kind of systems are called creeks. Then in rivers, then we have the artificial conveyance, that is, um, the canals for which are meant for the irrigations or water supply. And then in wastewater treatment plants also there are some conveyance structures. And then when there is a rainfall event, so water is flowing in the sides of the streets, so that is also under the purview of open channel flow. So let us look at the images. So here you can see that this it is a natural river which is flowing, so the water is flowing under the action of gravity. Here it is a man-made structure which is a canal, which you can see, so the water is flowing in the canal. And then you have a wastewater treatment plant. So here the waste is separated, and here also you can see that the open channel flows predominate. And finally, when you see this is a road, so this roadside, there are inlet gutters. So from here the water enters the inlet gutters, and that is also an open channel flow. So in unlike in pipe flow, where you observe mostly materials like steel or uh, what I can say, cast iron or wrought iron or similar materials, in case of open channel flow, the surface will vary very drastically. You can see here in the first image you have a rocky strata. Here you have a lined concrete channel. Again here you have concrete. Again you got a concrete, but all these are concretes are of different what I can say finishing. Here you can see it is much more finished product. Here it is but unfinished. Here you have an asphaltic pavement. So this kind of surfaces vary. Now usually there is a misconception that open channel flow has to be open from the top, but the open channel flows can also occur in conduits with a closed top, so such as pipes and culverts, provided that the conduit is flowing partially full. So you can see these are the pipes. So in these pipes also, the open channel flow can occur, provided this pipe, I mean, they flow partially full. So they should not be completely full, they should be partially full. Okay, so if they are completely full, it will be a pressurized flow. So examples are sanitary sewers and storm sewers, which have a free surface. So you can classify them as open channel flows only. Okay, so some characteristics of the open channel flow we may have a look. So the open channel flow, when we deal with this open channel flow, all the principles of fluid mechanics are applicable to the open channel flows as well. So whatever the energy equation, the continuity equation, the momentum equation, same are applicable here. However, the open channel flow is more complex than a closed conduit flow due to the free surface. So the presence of free surface increases the complexity. Now, whenever the forces which cause the motion and that oppose the motion, they should be balanced such that the free surface is a streamline along which the pressure is constant, and it has to be atmospheric pressure. So that is the requirement for an open channel flow. Now when you have a flow which is open at the top, so you induce another degree of freedom. That means your flow is not bounded by some boundaries, rather it is unbounded in one direction. So in case of pipe flow, it is bounded in all direction, but open channel flow in one direction is unbounded. So the flow can adjust itself given the different conditions. Now, as discussed earlier, open channel flow can encounter varied cross section and shape, because in nature you don't get a fixed cross section. Pipe, because you fabricate, you can make it circular, you can make it either square. Usually square are very rare, but circular or elliptical. But open channel can be of any cross section which is observed in the nature. Also, the roughness is different because the surface, it depends upon vegetation, the sediment size, and that is also different. Because of the free surface, the gravity is the main driving force in case of an open channel. So in case of pipe flow, it is the pressure which is the driving force, but in open channel, the gravity is the driving force. So it is defined by a dimensionless parameter, that is Froude number. So that is the ratio of inertial to the gravitational forces. So the inertial forces are represented by this are represented by this velocity. So here F equal to V upon the root GD. So this is velocity. This is Froude number. G is the acceleration due to gravity, that is 9.81 meter per second square. And D, this is the characteristic length. Or you can call it as a hydraulic mean depth, depending upon the surface. It will vary. So you can also call it as hydraulic mean depth, and it is a function of the geometry. So if you have a square channel, if you have a rectangular channel, if you have a triangle or trapezoidal channel, this parameter is likely to change. So when we deal with the open channel flow, our description will definitely involve the Froude number. Okay, so moving ahead. Now let us compare what is a pipe flow and what is an open channel flow. So as you can see in this figure, in case of pipe flow, so this is the pipe, and this is the center line of the pipe. So this is the center axis of the pipe. Now there are two piezometer tubes which are there on the pipe, that is at section 1 and section 2. And when we join this piezometer tubes, so the piezometer is nothing but the datum head plus the pressure head. So that will give you the piezometric level at these 2 points. Now in case of open channel flow, if you see that your free surface what exists, that is so in case of open channel flow, you can see that the water surface is itself the water surface itself represents the hydraulic grade line. So the again you can see this datum head plus the elevation of the water or the depth of water at that particular section. Now again the energy line, that is same, that you add the velocity head at a respective location, and during the course of the flow there will be some losses which will be denoted by a head loss. So that is very evident. So the main differences in a pipe flow, there is no the free surface does not exist, but in open channel flow the free surface exists. Now the pipe flow, since it is a confined flow, only hydrostatic pressure is exerted, while in case of open channel flow, the free surface is exposed to the atmosphere, hence atmospheric pressure is exerted. For a pipe, the cross section of the flow is fixed, and it is already defined, but for an open channel flow, the cross section and other physical properties may vary greatly. Now in pipe flow, since it is a pressurized flow, so the Reynolds number is a governing equation, while in case of open channel flow, the Froude number is a governing equation. Okay. Again, that we discussed that the water level in the piezometers represent the hydraulic grade line, and in case of an open channel flow, the water surface itself represents the hydraulic grade line. Now there could be a discussion point that what is a limiting case for the application of pipe flow vis-a-vis open channel flow. So that is a point upon which you need to ponder and think that where pipe flow cannot be applicable. However, open channel flow cannot be applicable at many places. Like I'll give you example. Let us say if you want to transfer water from lower elevation to higher elevation, that is against the gravity, you cannot apply open channel flow. But pipe flow is applicable there. Even pipe flow can be applied where the gravity is there, you can apply there also. So what is the case where the pipe flow cannot be applicable? That limiting case, you need to think about it. So let's move on to the next topic. Let us classify the open channels. So the open channels, now there are different kinds of channel classification depending upon how they are made, depending upon their cross section properties and all. So that we will see. So the first and foremost, we divide that open channels into two, that is the artificial and natural channels. So artificial channels everyone know, which are man-made, that is irrigation canals and stormwater receivers, and natural channels are rivers and estuaries. So that is a very straightforward classification. Coming to the another classification, we have prismatic and non-prismatic. This is very widely used. So a prismatic channel is one which has a constant cross section and longitudinal slope along its length. So you can see that this is a trapezoidal channel. Like that, we may have a rectangular channel also, a triangular channel also. So if the cross section and the longitudinal slope does not change, such a channel is called a prismatic channel. So usually your irrigation channels, they are prismatic channels. Coming to the non-prismatic channels, so non-prismatic channels, they are those channels either their slope or their cross section vary along the length. So they are called non-prismatic channels. So you can see that at section 1 you may have this cross section. At section 2 your cross section may change to this, and again at section 3 you may have a more deeper section. So like that, the cross section properties may vary, and it may also be possible that the longitudinal slope may vary. So initially it may have this longitudinal slope, then it may have this, again this. So like that, the longitudinal slope may vary, and that kind of channels are classified as non-prismatic channels. Coming to the other part, rigid and mobile boundary channel. So here we are talking about only boundaries. So a channel with immovable bed and sides. So here the longitudinal slope is not into picture, only the bed and side. So in this channel, these are the sides and this is called the bed. So this is called the bed. So the channel which have immovable beds and sides, they are classified as rigid boundary channel. Usually this, you can see in this figure, this is a concrete line channel. So this is a rigid boundary, so beds and sides won't move. So the concrete line channel, sometimes there are non-erodible unlined channels. So the channel may be unlined, but it is flowing into equilibrium that it won't erode the sides and the bed. That could also be due to presence of vegetation, and also the flow can be not large enough to erode that material. The mobile boundary channel can be channel where beds and sides are not constant. That is in case of an alluvial river. So alluvial river is which is more of clayey and silty nature. So there this bed and side will constantly change, and they will move. So from one location the particles are transported to other locations. So that is called a mobile boundary channel. So these are the basic classification of channels. Now let us move forward to classify the flows. Now before that, there comes a small question that since in rigid boundary channels the beds and sides are fixed, and in mobile boundary channels they are not fixed. So what can be the degrees of freedom in case of a rigid and mobile boundary channel? That needs to be thought of. So why this degree of freedom is essential to compute, so that we can, when designing such channels, we have to take into account which parameters will be varying and how to account that. So that is another thing which you need to um, discuss and answer it. Okay, moving ahead, we'll move to the classification of flows. So the very basic classification is depending on the variation with respect to time. So if the flow properties, so these are called flow properties, that is depth, discharge and velocity. So if the flow properties do not change with with time, they are called steady flow. And if the flow properties vary with time, they are called unsteady flow. So you can see for unsteady flow, del y by del t, that is change of depth with respect to time, is not zero. Change of velocity with respect to time is not zero, and change of discharge with respect to time is not zero. So these are called the unsteady flow. Steady flow, you can observe that flow in irrigation canals are usually steady, and flow in a river during floods is unsteady. That is, the depth, discharge and velocity may vary, and usually will vary in case of floods. Uh, Now, depending upon the variation in space, so space usually denotes length, because when we talk about one dimension, it is a length. So suppose you are standing at Indore and the river is flowing from, Simrol to Indore. So you have what to observe what are the variations in space, and based on that you can classify it to be a uniform or non-uniform flow. So in case of a uniform flow, your depth, discharge and velocity do not change with space, while in case of non-uniform flow, they vary with space. So that is why the derivative with respect to x has been shown. So uniform flow, there is a prismatic channel carrying a certain discharge and constant velocity, will always have a uniform flow, while the flow over a weir or flow downstream of a dam, there will be a non-uniform flow. Now these non-uniform flow can be steady or unsteady. That is another part which we'll be discussing further. Okay, so we'll again classify the non-uniform flow. So your non-uniform flow can be classified into three categories. Now, as discussed, it can be either steady or unsteady flow. That is a different case. But based on the non-uniformity in space, it is characterized as gradually varied flow, rapidly varied flow, and spatially varied flow. So as the word gradually suggests, so any variation that happens is gradual. So that is, the change of depth in this kind of flow is gradual, so that the curvature of streamlines is not very excessive. That is called gradually varied flow. So if the streamline is there, it will gradually vary. Now in case of a rapidly varied flow, the curvature is very large, so it can be something like this. In very small distance, there is a sudden drop or sudden rise in the depth, that is called rapidly varied flow. And in spatially varied flow, usually there is some amount of water which is added to the system and some amount of water that is removed from the system. So during the space, the water amount or volume is added or subtracted, that is called a spatially varied flow. In case of GVF, frictional resistance is very important, while in case of RVF, frictional resistance is very insignificant. So let us understand various cases of GVF and RVF. So as we can see, flow over a dam or a weir will be classified as a steady GVF. Steady GVF means GVF itself is a non-uniform flow, but the variation with respect to time is steady. So if you looking at this particular instant at time t equal to 0, then time t equal to 1, and so on. So the depth will not change at this particular instant. However, with respect to space, the depth is changing, but at that instant, the depth is remaining constant with respect to time. That is why it is called a steady GVF. That is flow over a dam or a weir. Now, in case of a flood wave, that is in a river, then it will be an unsteady flow, because flood itself is an unsteady event. So in case of a flood wave, it will be an unsteady flow. So let us say we are considering this section. So at this instant the wave is this way. After some time the wave can be this way or wave will be this way. So the wave nature will change, and that is why this will be unsteady. Now coming to RVF, the flow under a sluice gate. So this is a sluice gate which is generally used in irrigation canals. So whenever the flow, so here you can see this is the water depth, and when you just open the sluice gate, so sluice gate is lifted, the water will flow below it, and there will be a sudden change in the depth, which is represented by hydraulic jump, and that is called a rapidly varying flow. However, it is a steady RVF. But when you are looking at the other side of the sluice gate, so you suddenly close the sluice gate, there will be a wave propagation here, and that will be an unsteady RVF. So that is the difference between a steady and unsteady RVF. Coming to SVF, that is spatially varied flow. So you have a side weir. So in this side weir, so this is a longitudinal section and this is a plan. So there is a flow going, this is Q1, this is Q2, and there is some amount of flow which is being added. So in plan also you can see. So the resultant flow at Q2 will be some flow is removed, sorry. So resultant flow at Q2 will be Q1 minus QS. So the flow is subtracted, and that is called a spatially varying flow, and it is steady. The rate of flow is steady. However, in case of event of a rainfall, the surface runoff which is generated, so you can see that this is Q1 and this is the depth at this section, and this is the Q2 depth at this section. So here the flow is added. So the Q2 is greater than Q1 and the depth is also changing. So it becomes unsteady SVF. At a particular instant, if more flow is added, the depth will change. So that is an example of unsteady SVF. So if we look at a very broader picture, so this diagram summarizes it all. So this is a dam, or so you can see this is at this instant it is RVF. The streamline curvature is excessive. Then the depth is changing very gradually. Then it may be GVF. Then again it is RVF. Then again GVF, RVF. So like that, it is a synthesis of different flow conditions uh, along a single profile. Now, in case of a plan view, if you see, then this is the main river. This is a dam which is constructed. Downstream of that, again, there is a main river which is going. Then there is an off-taking canal. There is water being added from a tributary. So here, your SVF condition can be visualized. Okay, so the way you see all these aspects, it becomes more and more clear. Coming to the next part, which gives us some well-known classification of the problems which we can encounter. So the open channel flow, we can see that there is one category which is uniform flow. Second, we see there is a non-uniform flow. Under non-uniform, we have a steady, we have unsteady flow. Okay, so again, under steady non-uniform flow, we have steady GVF, RVF, SVF. Again, unsteady, we have GVF, RVF, SVF. But one category we could not see here, that is unsteady uniform flow. Now, why we cannot, or is there a place where we can see this unsteady uniform flow, or what is the basis of it? So that we have to answer the question, that where we can observe this unsteady uh, uniform flow. That is your challenge. Now, the third classification, that depends upon the direction of flow, where we intend to see the variations or analyze the variations. So one dimensional, see, usually flow is a 3D structure, but depending upon the different cases, we can see which effect is more predominant. So when the velocity variations are in the cross section are neglected, and average velocity is taken, and the velocity variation along the length only is considered, that is called a one-dimensional flow. So flow in a river, where only along the length you analyze what changes are going on, and that is called as a one-dimensional flow. In case of a two-dimensional flow, uh, when your channel is very wide in relation to the depth, the velocity at a given elevation would be constant, and it will be independent of the distance from the side wall. So if this is very wider section, if this width is very wide, then this kind of case will occur. So usually flow in canals. And three-dimensional flow, in which the velocity is dependent on the location as well as distance from the point from the bed and the side wall. So there the three-dimensional. So in case of a narrow channel, it is very much applicable. So here if we see that the velocity variation in case of a one-dimensional flow, it will be just with respect to the length. So here I have given the sign convention: x is the length, y is the width, and z is the depth. So velocity is a function of length only. In the case of two dimensional, it is a function of length and width, and three dimensional is a function of length, width, and depth. So all these three can be visualized. Okay, and lastly, coming to the classification, that is depending upon the viscosity of flow. So it can be classified as laminar, transition, and turbulent. So you have already studied this in fluid mechanics, so just a quick recap. So in laminar flow, your viscous forces are more stronger compared to the inertial forces, and in case of turbulent flow, the viscous forces are relatively weaker compared to the inertial forces. So in case of laminar flow, the water particles appear to move uh, in an ordered manner, like in a streamlines. So, and in case of uh, turbulent flow, water particles move in a random and irregular manner. Okay. Similarly, for Reynolds number to be very small, you will observe laminar flow, and Reynolds number to be very high, you will observe turbulent flow condition. In between these two, there exists a transition state. So you have a Reynolds number R equal to rho Vd by mu. So this is rho is the density, V is the velocity, D is the characteristic length. So in case of pipe, circular pipe, it is the diameter, but in case of rectangular or trapezoidal channel, it will be different. And mu is the kinematic viscosity. So that way you can work out the Reynolds number. So usually you know the Reynolds number range for flow classification. If it is less than 2000, you will classify as laminar flow. Greater than 4000, you will classify as turbulent flow. So whether these values can be extended to open channel flow or not, that is the point we have to think upon. Okay, so with this we come to end of our first part. So you go through all this and we'll discuss the velocity, velocity distribution, pressure distribution, governing equations of open channel flow in the next part. So thank you everyone.